Good afternoon. Okay. At least you're talking, that's good, because this morning I felt like they were in shock still, okay? That was not my intention to put you in shock with that midterm, okay? Maybe we should discuss this a little bit. Don't look at the percentage. Forget about the percentage, okay? It doesn't mean anything, percentage. I cannot, on B-Space, in the gradebook, I cannot throw it out. There's no way to get rid of these percentages. Ignore the percentages. Just look at your points, okay? And at the end, you add them all up, and then you get your grade. That's how it is. So you have, for each midterm is worth 120 points. The final is like 2 midterms. You have 3 hours, and it's 240 points. But it will also have not double the amount of questions, okay? It will not have double the amount of questions, because the lab, you get maximum 250 points. For the homework, you get 150 points. That gives a total of 1,000 points. And then you get, for the iClicker, if you were there all the time, you get 50 points. Everything else will be prorated, okay? So you get 1,050 points, but I only grade you on 1,000 points. So that means if you have 850 points, you have an A, up to 1,000 points. Of course, there will be pluses and minuses, and the minuses and pluses are at my discretion. This is sort of a little bit of on a curve grading, then, and that's how I look at it, okay? The B will be 849 to 730 points. The C will be 729 to 580 points, and the D 579 to 430 points, and the F smaller than 430 points. We won't have any of those here, hopefully, okay? And so this is clear now. Forget talking about percentages and A plus and B minus and whatever. You can't know that at all until you have added up your points. So you can project your grade. That's what you can do, okay? If I do that well in the homework, I get all these homework points. If I do that well in the lab, I get these lab points. So I can have the maximum of 250. And if I need, in the final, I need that many points to get that grade, all right? So there's no need for panic. There's still lots of points to be had. All right? Good. Don't stop focusing. So the last time you focused on equilibria, and it's just a continuation of what we did, acid-base equilibria. And what you were talking about, if I understand, so you are, especially some of you in high school, they learned if you have a substance, and you put it in water, if it releases protons or hydrogen ions, then it's an acid, okay? And if you put another substance in water and it releases OH minus ions, then it's a base. This is what Arrhenius did, okay? Many, many hundred years ago. And so I used that word protons and hydrogen ions and hydronium ions and H plus. I use this interchangeable. It's all the same, okay? So a proton is, of course, a hydrogen ion, yeah? And H plus is a hydrogen ion. HVO plus is a hydrogen ion that has gone onto H2O, all right? In chemistry, very often you don't write H2O into the equation. You just say HCl gives H plus Cl minus. Of course, it's not correct because you need the water in there in order to balance it properly. But that is the slang we use, all right? Don't get confused by that. So of course we're using slang. Every language uses slang, and we're using the language of chemistry here. We have our own slang. So you talked about, that was the Arrhenius theory of acid and base, but that was the one which makes OH and makes H+. But then along came these guys, Brønsted, and who was the other guys? Who was the other guy? Laurie, okay? Laurie and Brønsted, and in the 30s of the last century, they decided by looking at an acid is actually something that donates protons to something else. And a base is something that receives protons, that takes protons. That's the new definition, and that's what you need to do. And so with this, you have an acid is HA, and it's with a base. That base wants that proton here, okay? So the acid gives that proton because it's a strong acid, so it really doesn't have any tendency to hang on to its proton. It wants to give it away because it's a strong acid. So it gives that proton to that base, and suddenly the acid becomes its conjugate base. It becomes the anion. That's the conjugate base of the strong acid HA. A minus is the conjugate base, all right? And the base now wanted that proton. It took it, and with this, the base became its conjugate acid, BH+. So for this, you can now, if you do this in water, you have acid, you have a strong acid, and it has to be in water to be acidic to deliberate these protons. So it reacts with water. Water acts as a base. So that water here takes that proton, or no, the acid gives that proton, or the H ion here, to the water, and with this, the water becomes HVO+, okay? So water is the base. It receives that proton, and now it becomes itself an acid, and we call this a conjugate base-acid pair. So the acid has now given away that proton, and by doing so, it became a base, okay? You think that is a very strong base if you have a strong acid? Anybody? No, why wouldn't it be a strong base? Because then it would do what? Okay, if this is a strong acid, okay, and this becomes this here, okay, that acid, is that a strong acid? No, it's not a strong acid, because then it would like to give that back to the conjugate base to form the acid again. But strong acid, what does it mean? It means that the K, and you all know now what the K is larger than 1, much larger than 1. What does this mean? The equilibrium concentration of a strong acid, you have all products. There's hardly any reactants left over. So that's the K larger than 1 is the definition of a strong acid, all right? It completely dissociates in the H and the A minus, or as we say here, in the HVO plus and the A minus, completely, okay? So, and the same is with the base. You have an acid, so you have a strong base. The acid gives its proton to the base. The base wants that proton, okay? That's why it's a strong base. It wants that proton, so it takes it, and the base becomes suddenly BH+, and that's its conjugate acid. So the base and acid pair, they're always amongst themselves. The acid has a conjugate base pair, and the base has a conjugate acid pair, all right? That it has a conjugate acid, and they're forming a pair. Let's do this right, okay? They're forming a pair. And so you see here that base wants that proton, it takes it, gets BH4+. Now, is that a strong acid now or a weak acid? That's a weak acid, because if it would be a strong acid, it would give it back to the original acid, and this is not what we want. So that H2O, which acted as an acid, the water, suddenly became a base, and now that's very visible, OH minus. We know this from our common understanding, OH minus is a base. Now with this, you have now, this is an acid equilibrium, and this is a base equilibrium. The acid equilibrium, you're right, concentrations of products, concentration of A times concentration of HVO+, divided by concentration of reactant, HA, divided by H2O. Why didn't I write H2O here? It's the pure phase, it's in water, so we set this as 1. So that is, you can omit that 1 here from this here, okay? So this is our acidity constant, and if this is larger than 1, then you have a strong acid. That's all you need to know. So, and with the base, so we do the same thing. We do the concentration of the product, OH minus concentration times BH plus concentration divided by the reactant, that's the base, divided by the concentration of B, divided by H2O, but H2O is pure phase, is 1. With this, we can omit it, okay? So now we have defined an acid constant and a base constant. We call this Ka, and this is Kb. That's for acid, and that's for base. Now you then looked at water. I'm repeating what you... Do you know all this stuff already from the last lecture? You totally got this the last time? Or shall I continue, or shall I go on? Continue with the review? Yeah? Okay, good. All right. I don't want to bore you, okay? And so you have water, and this is it's not funny, but it's kind of strange. Water can act as an acid and a base by itself. You have H2O can be an acid or can be a base. So if it's an acid, what does it do? It gives the proton to the base, and with this, the base becomes its conjugate acid, and the original, the water, the acid, becomes its conjugate base. Now you can do the equilibrium constant for this. K water is the concentration, this is the K for this, concentration of products, OH minus, times concentration of H3O plus, OH minus divided by times concentration of H3O plus, divided by concentration of water, divided by concentration of water. But what is the concentration of water? 1, okay? So you have now, this is the equilibrium for the auto-dissociation or auto-ionization of water. That's what water does. It has that equilibrium, okay? And this constant Kw is at 25 degrees is 10 to the minus 14, okay? With this now we know if this is 10 to the minus 14, I take the square root out of this, then I get the concentration of H3O plus, which is equal to the concentration of OH minus. And I take the square root out of 10 to minus 14, what is it? 10 to minus 7, okay? So that's this 10 to minus 7, and with this I have a definition for my pH. But actually, the P definition is something which you have learned. You can make a P definition of anything, okay? Let's say I have an acidity constant of 10 to the I have a constant, any equilibrium constant. Let's say that equilibrium constant is 10 to the minus 11, to make it easy, okay? So I say, okay, to make a pK out of this, I say, take the logarithm of this. What's the logarithm of 10 to minus 11? It's minus 11, and multiply it with minus 1. Minus 11 times minus 1 is plus 11. What's the pK of this? Is 11. So if I would have a pK of 10 to the minus 14, no, a K of 10 to the minus 14, what would be the pK? Okay, don't get fooled, because the pK gets larger as the constant itself gets smaller and smaller, okay? Don't go in the wrong direction when you see pKs. Think, that's the first thing you have to do, think, okay? So with X as a concentration, for example, I can determine, I take the log of the concentration and multiply with minus 1, then I have a P of concentration. So the same thing I can do with the concentration of hydrogen, and then I call it pH, because that H stands for hydrogen. Correctly, I should call it PHVO plus, but it's, so you have that I wrote it H3O plus, so that would be the pH, would be then the logarithm of the H3O plus concentration times minus 1. And what is at neutral when you have water? Neutral water is pH 7. You have 10 to minus 7 moles OH minus and 10 to minus 7 moles H3O plus. So you know that your concentration of H3O plus is 10 to minus 7. You take the logarithm of this. This is minus 7. You multiply it with minus 1. You have pH 7. That's neutral, okay? That's water. That's neutral. pH 7. So this is, and with this, if I give you, for example, a pH, and I give you the water constant at 25 degrees, the equilibrium constant for water, what is that at 25 degrees? Water, Kw at 25 degrees, anybody? It's right here, isn't it here? 1 times 10 to minus 14. So you could calculate the pOH because it's just 14 minus that pH, okay? All right, so let's say we have a concentration of 10 to minus 1 molar strong acid. What's the pH? Okay, logarithm, 10 to minus 1 is 0.1 molar, okay? 0.1 molar. Logarithm of 10 to minus 1 is what? Minus 1 times minus 1. What is the pH? Positive 1, okay? It's positive 1 here. And the pOH would be, so that positive 1 would be 10 to minus 1 here. No, that would be, no, I'm talking about here, about 1, okay? Now, let's say we have a 1 molar solution. What would be the logarithm of 1 is what? 0. Okay, you're sure about that? Okay, is 0 times minus 1 is still 0. Okay, with this your pH is 0. And that would be your pH is 0, that is 1 molar, your pH is 0. Your pOH is 14. Okay, pH plus pOH gives you pKW. All right? And now let's say we have a 10 molar acid solution. 10 molar acid solution. Very strong acid. There are acids that which can be 10 molar. What's your pH? Negative 1. Did you think that the pH can go negative? Yes, it can. If you have a 100 molar solution, it would be negative 2. Okay? But unfortunately, we don't have acids that strong. But 10 molar we have, so you would have a pH of minus 1. So if you have a 10 molar sodium hydroxide solution, I think it's not soluble, let's assume 10 molar sodium hydroxide solution. What would be the pH? What would be the pH? So the pOH, what is it? If you have pOH is what? The pOH is 10 molar is negative 1, isn't that right? And 14 plus minus 1, what is that? 15. Minus 1 is 15, okay? So that's the pH would be 15. So we just, for convenience, we tell between 0 and 14, but you can have a pH of 15, you can have a pH of minus 1, okay? It's a logarithmic scale. It's all theirs, okay? And so this would be, for example, a solution of 1 molar OH would be 1 molar OH. It's the log of 1 is what? 0, okay? So that means the pOH is 0. With this, the H plus is what? H plus is 14, exactly. 10 to minus 14, we take the log of this, times minus 1 is 14, that would be 14, okay? I hope you got the hang of this. So, now then you took the titration of a strong acid. Strong acid, what is the K for strong acid? Greater than 1, okay? Greater than 1. So, of course, you don't know what the acid is. You know it's a strong acid. But I tell you, in this case, it's 0.1 molar HCl per liter. Now, but if you have 0.1 molar, that means already per liter. So this is superfluous. So that should have to be a small m, actually, moles per liter. All right? The large says already moles per liter, actually. I just noticed that. So you start out, what is the starting pH? This is your pH, and this is the amount of 0.1 molar sodium hydroxide that you have added. What is your starting pH? 1. Okay? And I have a 0.01 molar HCl solution. What is the starting pH? 0.01. 10 to minus 2. What's the starting pH? 2. Okay? 10 to minus 2, log is minus 2, times minus 1 is 2. Everybody got that? I don't want to hear the biologist telling me like what happened this year, I think, or last year, but it was with the people in the fall. It was not my people. They said, these guys don't even know pH, they said, okay? And I said, not my guys, okay? So that's why I went through this with you. If anybody comes to and they really ask about pH, you need to know that, okay? Anybody, that's sort of common knowledge of the man in the street, actually, since you are not the man in the street, so you don't have to know it. All right, so now you're gonna you're gonna add 0.1 molar sodium hydroxide. Now each H3O plus sees an OH minus and forms water. Molecule, we go up. Well, so we eat up that H3O plus, and we make water out of it. What happens to the pH? Does it go up or down? Up, okay, the pH goes, so that's what you see here. And then we come at the point where the concentration of OH minus and H3O plus is the same. What is that point? Equilibrium, and it's the neutral, the equivalence point. So where would that be? Where you have the concentration of OH minus and H3O plus the same? pH 7, because this is exactly this condition where you have the water, that's it. So this is our equivalence point here, and this is at 7 for strong acids. And now you're going to keep adding OH. So the H3O plus and the OH still, the H3O plus goes down and the OH goes up, okay? Till you, at the end, you have essentially 0.1 molar sodium hydroxide, and you are close to pH 13, all right? You can do the same thing in the reverse order when you start with the 0.1 molar sodium hydroxide solution, and you start at pH 13, and you go down, and your equivalence point is also 7, and because this is the same thing, water, you're making water, and so this is the titration curve for a base. Greg has detailed this very nicely for you. I just want to make sure that you guys know this, okay? This is such a fundamental, I was about to say such a basic thing, but it's not basic, okay? It's fundamental. Otherwise, I would have to say such an acidic thing, but that would be not fitting. All right? So let's see if you understand. We have a titration curve where we titrate. This is the amount of titrant we added. And this, you need to know what this is here. We titrate with 0.1 molar sodium hydroxide. We get this curve here, okay? So you have to think what this is here. You probably know that. Now we take a new solution, but the same solution, same acid solution, and we titrate it with 0.2 molar sodium hydroxide. Suddenly, the sodium hydroxide is twice as strong than the first one, okay? So would the titration, and this is the green curve, would it be A, B, or C? Why don't you think about it and then try to give me a good answer? You having the discussion already? Okay or not okay? So think about it. Did the HCl concentration change before you did anything? You haven't started titrating? Did the HCl concentration change? Okay. It didn't change, all right? So that eliminates already some of them, okay? And then your base is now twice as strong than the one was before. You go molecule by molecule, H3O plus neutralized by OH minus, okay? So, but now you are more concentrated. Your base is more concentrated. What does this mean in terms of volume? You're plotting your volume here. And why don't you discuss this with each other? Lively discussion, and give me your answer, please. You got it, huh? What is it? Hmm? Yes! Excellent! Good, you're getting the hang of it. Or at least your neighbor did. Okay, so what you do, this one here, you haven't done anything. This is the pH here, okay? We did this ad infinitum. This is the pH. Forever we have discussed this, ad infinitum instead, okay? To infinity. What is infinity? Okay, so this is the pH, so you haven't done anything. The HCl, you haven't done anything to it. It should have the same pH. So this you can forget. Now you have these two, okay? So you would add base here, and actually the same would happen than if you put one molar base. You think this is right? Your base is twice as strong than it was before, so that means per milliliter, you're adding twice as many OHs in there. So that means you need half the amount of volume in order to get to your equivalence point. And this would be C here, and you get your equivalence point here, but you come with half the volume into it. And this here tells you a little bit more also. It's a little higher because you have now 0.2 molar, which is more basic, and with this, the final pH also would be a little higher than this one here when you had 0.1 molar. So let's see, the equivalent points is reached with 1/2 of the volume, and the answer was C. Now, let's come to weak acids. And who can tell me a characteristic of a weak acid without even having heard about it, okay? That's not it. That's it, okay? Who can tell me what the K of a weak acid is? Less than 1. And the pK? Greater than 1. Excellent, okay? And so weak acids are a bit tricky because a weak acid is, for example, acetic acid. We say this is for the acetate. It is an acetate ion with an H on it, okay? So, and the H, we call this, it's acidic, it can go off, okay? It acts as an acid. And so you have acidic acid, and it reacts with water. So this is our acid here, okay? So what does it do? Gives the water, the proton or the H plus to the water, and the water becomes then H3O plus. So that's the base. It becomes its conjugate acid, and then this one here has given off the proton, and it's now its conjugate base, okay? And so this is the acid, and this is the base here, okay? And then we have the base, and it becomes the conjugate acid. So with this, we can have a equilibrium constant. Concentration of this times concentration of this divided by concentration of this. I don't have to talk about this anymore. So this is 1.8 times 10 to minus 5. So what do you think the pKa would be around? Between 4 and 5, wouldn't it be? And so the pKa is 4.7, all right? You can also say it's 10 to the minus 4.7. And then you punch in your calculator and let it calculate, and you get the pKa number, all right? That will be your calculator, will spit this out then. Okay, so if it would be a strong acid, everything would be wonderful. But it's not a strong acid, it's a weak acid. So now this baby here, that base, reacts with water. There's a second reaction. That base reacts with water, and so the acetate ion, what is that now? It's a base, and reacts with water. Okay, it takes a proton from the water. Now it becomes undissociated acetic acid again, and the undissociated acetic acid is the conjugate acid to the base initially, and this is the acid here, and it becomes OH minus. OH minus, that is a reaction that is basic, obviously. So OH minus is the conjugate base, and the acid was the base, and it becomes the conjugate acid. So now this is even the equilibrium is even smaller for this. Now this would be, because this is a base now, we're making this here, this is a base equilibrium. So the concentration Kb, we call this for base, the concentration of this times the concentration of this divided the concentration of the free acetate ion is 5.6 times 10 to minus 10. Very small, okay? And the pKb is with this 9.3, so that's a much smaller number here than this here in terms of the K. Now, what would you think if you have 0.1 molar weak acid and you compare this to 0.1 molar strong acid? Okay? So what do you think? Would the pH of the weak acid be larger than the one of the strong acid or smaller than the strong acid? Why would that be? Anybody? Why would be the pH higher? No, because you have this here. You're suddenly making this here, okay, and this increases your pH. The pH goes up. So you can say already, if you have two weak acid and a strong acid at the same concentration and you throw it in water, okay, the pH of the one that is the weak acid will be higher than the pH of the strong acid. Okay, that's the first thing. Now, of course, we can do the same thing for a weak base and acid equilibrium. Our base would be this here, NH3, that will take a proton away from the H2O. With this, you have NH4, its conjugate acid, NH4 plus, and this H2O was now the acid, and it becomes the base OH minus. Now we can, would we do an acid constant or a base constant for that? Base constant, of course. The base constant, concentration of this times concentration of this divided concentration of this, is 1.8 times 10 to minus 5, okay? All right? So if I take the log of this, multiply it with minus 1, it's 4.7. That's incredible, actually. That's just by chance here, okay? That this is 4.7, this is 4.7. This is just how it is, but it has nothing, there's no connection to it, okay, with these numbers. And so now what happens? This one reacts, one of them needs to react now with water. Okay, of course our acid reacts with water. Now the acid becomes its conjugate base, drops that proton here to the water, and the water picks it up. Now the water acts now as what? The water acts as base, and it makes its conjugate acid, and the ammonia was the acid, and it gets its conjugate base, and with this now you can, what is this? Is it an acid or a base equilibrium? That's an acid equilibrium. And concentration of this times concentration of this divided concentration of this is 5.6 times 10 to minus 10, and we know already this is 9.3. Again, these are the same numbers, totally random, okay? Have nothing to do with each other, right? All right? So this was, so if you have a weak base and you have a 0.1 molar solution of a weak base and a 0.1 molar solution of a strong base, which one has the lower pH? The weak base, exactly, because you make an H3O plus, which eats up some OH minus, and with this you drop the pH downwards, and it becomes smaller, and with this the acidity increases. Good. Let me see if you understand. All the equations that you need for this baby here, for that, I mean the chem quiz, are on here. So I have a 0.1 molar solution, and I'm asking you which has the highest pH. Is it sodium acetate? That's a salt, okay? It makes obviously sodium and AC minus, sodium plus and AC minus. Ammonia, you know already what that is, okay? And ammonium chloride is also a salt. It dissociates in NH4 and Cl minus, all right? So now react it with water and then write your equilibria and look for the constants, and you can answer your question. Which one has the highest pH? Well, highest pH means also the least amount of H3O plus or the largest amount of OH minus. All the equilibria that you need are up here, okay? So this dissociates in Na plus and AC minus. This dissociates in NH4 plus and Cl minus. I was supposed to fly to Europe tonight. Did I say that already? No, huh? I said it to you guys, okay. So I was not planning to teach next week, so there was Greg, but there's this volcano that erupted in Iceland, and now it's produced this huge cloud of volcanic ash, and it's now at 25,000 feet altitude, 25 to 30,000 feet altitude, and all the airports, nearly all the airports of Europe are closed, no flights going out of the States. The longest cancellation, the highest cancellation number we ever had since 9/11. So they don't even know when it's going to be dissipating. It might come back, actually. So that was to be expected. So now, if this here, the sodium, would that do anything? The only thing that could do something would be that AC minus, okay? Why don't you find that AC minus here, and then you look at the equilibrium. With this, you have your constant, okay? You know what the OH is here. This NH3, what is that? It says right there, okay? That's the equilibrium. And then NH4Cl dissociates into NH4 plus and Cl minus. What does the NH4 plus do with the water? It's also up here, okay? So now look at it and give me your answer. Discuss it with each other, please. So what is it? I was... So what's the answer down here? Oh, by the way, yesterday I spent an hour with the German Chancellor, Chancellor Merkel. We had an hour of discussion, 15 scientists from the Lawrence Berkeley Lab, and she's a very bright woman, a very good chancellor, obviously. She knows exactly what's going on, but politics obviously are a different game. Okay, so yes, I agree. I think it's B. No, I don't think. I know it's B. Okay. I shouldn't say that. I think people don't trust me then. So, which one is an acid? Is NH4 plus and Cl minus? Is this a base? So NH4 plus, what is NH4 plus? It's an acid. It makes its conjugate base, has an acidity constant, so it's 5.6 times 10 to the minus 6. It's a very weak acid, but it still is an acid, okay? Now, what is sodium acetate? Sodium acetate is a base, okay? It reacts with water. The acetate reacts with water to form acetic acid and OH minus. So that's a base, but it's a very weak base because its constant is 5.6 times 10 to the minus 10. So the equilibrium is very much on this side, not very much OH produced, which would bring the pH to higher values. And the last one was NH3. NH3 is a base, reacts with water to make OH minus, and NH4 plus, the conjugate acid of that base. And the Kb, the base constant, is 1.8 times 10 to the minus 5. Okay, this is much stronger than 5.6 times 10 to the minus 10. And with this, the answer was NH3. And here are the equations again. NH3, this is 1.8 times 10 to the minus 5. This is the acetate that reacted here after dissociated. That was an acid constant. It was a base constant, yeah, right, that's a very weak constant. And the acid constant was this one here, NH4 plus, reacts with water to form NH3 and H3O plus. And this was also, what was that? 5.6 times 10 to the minus 10. That's just pure chance that it's the same, okay? It has no connection. And with this, your answer, the largest Kb has the largest OH production. With this, the answer was NH3. Okay. So now, we have a weak acid, and we look at that weak acid here, and it dissociates, and the equilibrium obviously is not totally on the right side. It's a negative number. K is smaller than 1, and not negative, but K is smaller than 1. And with this, we have here, we can a Ka, concentration of this times concentration of this divided by concentration of the undissociated acid. Now we look at this one here now, and this reacts with water. That's the second step. It forms undissociated acid plus OH minus, and you get a base now, a base constant, HAC plus OH minus times OH minus concentration divided by AC minus concentration is KB. Now what happens if I multiply this here? If I multiply these two, I say Ka times Kb equals, so I multiply this one cancels here, okay? This one cancels against this one, so Ka times Kb is H3O plus times OH minus. What is that? Kw. Okay, Ka times Kb is H3O plus but OH minus is Kw. That is true for weak acids and weak bases. Okay, now I give you, for example, a Ka, and what's the Kw for water at 25 degrees? 10 to the minus 14. With this, you could calculate what Kb is, or vice versa, because you have three unknowns, three things that you want to know, and two of them you know, so the third one will be easy then. And so this is, we have an acid-base pair, and now let's do a base-acid pair. So our base was NH3 plus, forms NH4 plus and OH minus, and the Kb is this concentration times this concentration divided by this concentration, okay? And now this one here, the NH4 plus, is now an acid and reacts with water to become its conjugate base. And with this, you can have now an acidity constant. It's this times this concentration divided by this concentration. If I multiply this, I have Ka times Kb is NH3. NH3 is canceled here. This cancels. The NH4 cancels here. This is OH minus plus H3O plus. So that means Kb times Ka is K water. And this is 10 to the minus 14. Does the number increase? What happens to the pH of water if you, at 60 degrees? Does the pH get higher or lower? Lower. How do you know that? There was a chem quiz last time, okay? Good. It's only 10 to minus 14 at 25 degrees. It was 10 to minus 13 at 60 degrees, okay? And KOH minus times H plus is 10 to the minus 13 at 60 degrees. And with this, your pH is the square root out of it with 6.5. Don't go yet, okay? Now, we have two acids, HA1 and HA2, okay? And this is the pKa1 for HA. The pK is smaller than the pKa2, pKa, okay? Which is true if I react HA, the acid 1, with the A2 minus, HA2 gives HA2 plus A1 minus. Is K smaller than 1, equal to 1, or larger than 1 for that reaction? You have the individual reactions of those guys here. And so what is it? Smaller or larger? Or equal? You have to ask yourself, which one is the stronger acid? Is it HA1 or HA2? Which one is the stronger acid? That's the one that likes to give of its proton much more than the weaker acid. Okay, so you have time to think about this over the weekend. And this is what we do on Monday morning then. We're going to pick up right there. So you need to know pKa, that means AHA is the stronger acid. Okay? Think about it. And the solution on Monday morning, the solution. See you on Monday. Have a good weekend.